So a classic example of an application involving a first-order linear ODE is a mixing problem. So the idea is that a solution of some sort is flowing into a tank at a rate R in, and it's flowing out at a rate R out. So here's the incoming R in and the outgoing R out. Now, both of these are in units of volume per time, because we're talking about the volume of the solution. What we're going to do is set up, we're going to look at the mass of the solute and call that x of t. And we're going to set up and solve an ODE for the solute, not for the solution. So it's important when setting up problems of this type to keep track of whether you're doing stuff for volume, which is solution or concentration, or solute, which is going to be mass. So let's see. So over here in our vat, we have x of t, so that's going to be the amount of solute that's been dissolved in there. And then there's going to be v of t, which is going to be the volume of solution. And so these rates are both in terms of volume per unit time, because that's what you could actually measure in a laboratory. You could determine how much fluid is flowing through the pipes. You can't actually determine how much, dissolved whatever is flowing through the pipes. So the idea is that the solution, this is a solid, suspended, or dissolved in a fluid. And so what this corresponds to is the idea of concentration. And when somebody's talking about concentration, they're talking about the mass of solute per volume of solution. Okay, so what that translates to then in symbols is that the concentration at time t is going to be x of t over v of t. And so we want to set up our ODE for x, not for c. If you try and set it up for c, you're doomed. Okay, so then let's see. So in addition to the rate in and out of the fluid, we also have the concentration of the incoming and the concentration of the outgoing. So I'll label both ends of the vat with that. And then we can see that if you look at R times C, either for the incoming or for the outgoing, dimensional analysis reveals that we're looking at volume per time times mass per volume. And so if we cancel these, then this gives us mass per unit time, which is the appropriate quantity for talking about time rate of change of mass. So we're going to be setting up the ODE for dx dt. Okay. Now, the basic conservation law is that, and this is used throughout physics and chemistry and whatever else to set up things in terms of a differential equation model, is that the time rate of change of the thing that you're interested in is equal to what goes in minus what goes out. So that's all that this equation is saying here. This is just rate in times concentration in. That will give you the amount of incoming mass minus the rate out times concentration out. That will give you the rate of outgoing mass. Okay, and so in terms of the things that we have already set up, let's take another look. So coming back here to the tank right here, the concentration of whatever's coming in, that'll be given as part of the data of the problem. The rate at which the tank is being drained, that will also be given as part of the data of the problem. But the concentration of the outgoing, this is actually something that you can determine, because the concentration of what's coming out is the mass divided by volume of whatever's currently in the tank, and those are quantities that we hopefully have some understanding about. So coming back to our setup here, we have that the concentration of the outgoing is the concentration in the tank, so that's x over v. Okay, so setting up our differential equation, then we have dx dt is equal to R in, C in, minus R out, and then C out is now replaced by x over v. And so if I take this term and put it over on the other side, then we see that this is dx dt plus R naught over, sorry, not R naught, R out over v times x is equal to R in, C in. And so here we have a first order linear equation. There's our P and there's our Q. So this can be solved by the method of integrating factors.